20 years ago in response to Mars Direct, and 20 years has gone by. There's a lot of new ideas and new concepts that have come in. Validate Mars Direct, but all ideas advance and evolve with. You take the best parts of Mars Direct, which is the redundancy and the fact that you can produce materials on Mars for things, and then you add the new ideas and you get something better. And the things I'm going to focus on is the service of Mars expeditions, and do we know how to land humans on Mars, and how do we do it? And I'm going to go over some of the other stuff fairly quickly. And this is pretty important, looking at the kinds of Mars expeditions, but focusing on the flags and footprints versus Antarctic-style scientific basis. Most of the versions of Mars Direct proposed so far use all expendable vehicles. And how do we do some things we need to do? We will be able to do on Mars in 10 or 20 years. So why don't we want to do flags and footprint missions? Well, everybody who lived through Apollo, I think, has a gut knowledge of why. Because if you do a flag and footprint architecture, you get a flag and footprint mission, and then you have a big interregnum where nothing happens for a couple generations. And I think, like I was in college when they were going to the moon, and I've now retired, and they're still 10 or 15 years from going back to the moon. So we don't want that to happen again. So what's the answer? You have to go to assist initially. The very first time you go to Mars, you want to have a system of reusable spacecraft, reusable launches, reusable whatever. A very specific situation why you can't or don't want to do a reusable something. I'm going to go through these pretty quickly. I go through a real quick list of the some of the different kind of reusable first stages, clusters, where they all come down individually. Clusters where they fly back, clusters are single large rocket that flies back to a landing strip, single large rocket that lands vertically on its own, like the old Phoenix Gary Hudson concept, a fully air-breathing hypersonic booster. And notice the most important thing is the lowest operating cost versus the development cost. It's critical. These are just concepts of clustered boosters showing that you can cluster almost anything no matter how big it is. The key here is the wider the better. You'll see why wider is better. Minimum 10 meters, 33 feet, like the size of a Saturn V. This is a flyback system that Hugh Davis and Buzz Aldrin came up with called the Starcraft Star Booster. And I'm going to gloss over that. Everybody knows what the problems with the solids are. I'm going to get to the interesting stuff here. Reusable, minimizing refurbishment. Flexible payload mass if it's a cluster, wide payload shroud, minimum 33 feet, large payload shroud volume to hold large integral structures with low density, and ability to recover the second stage if possible. And this goes into some of the stuff of building up the Mars fleet. The Vasimir I'm going to skip over, people have heard about it. You do need a very large power source in the megawatt range to make it work. I think that Vasimir is very important, but again, as Bob says, it's useless without the very large power source. We still need a large power source for space missions, a very compact power source, not just a large power source. There's a difference. There's a Vasimir image. Okay, so understand that when you're re-entering, that's aero braking. When you're aero capturing, it's also aero braking. Anything where you're using the atmosphere to slow down, aero capture or a cold aero capture. is still an aero braking. It's still an aero braking. So let me go to the diagram, which is a little easier to see. Aero capture means you're coming in from an going through Mars one time in a very controlled altitude, going out to an apogee, doing a small, doing a very large at all. That saves enormous amounts of fuel. Generally, the aero capture aeroshells are not an integral part of the vehicle. They can be, they don't have to be. They're usually very large. There's a picture of an aeroshell doing an aero braking maneuver as it approaches Mars. And this talks about some of the things, even with Mars Direct, you're still going to need some kind of a depot-like system to get that liquid hydrogen to Mars orbit from Earth orbit. And if you look at the middle there, what you need is ability to transfer and storage the propellants without loss to boil off using sun shields, super insulation, and cryocoolers, which is active cooling of the propellants using solar power. If you have all the other protection systems, you're not going to have that much boiling off, and a small amount of solar power would do what needs to be done. Here's an example of a depot using a sun shield, and the hydrogen tank is behind the sun shield. The oxygen tank would be in front of it. And these are some other concepts, Boeing concepts for depots, multiple large capacity ones. This would be taken to Mars orbit from Earth orbit and behind a very large aero capture and delivered into Mars orbit with a large volume, a couple hundred tons of liquid hydrogen for this kind of mission. And you need to build up what is essentially a base in Mars orbit to operate from with a fairly large crew. If you have reusable vehicles to get the stuff into Earth orbit, it doesn't cost billions of dollars per mission because you're reusing all the equipment. Even the Earth to Mars and Mars to Earth vehicles are all reusable because they use aero capture to get back into Earth orbit too, instead of just going down and landing like an Apollo. So the case for reusable Mars ferries, if your number of ferries need to be built and shipped, allow swapping of individual equipment modules. Be used for asset saving mass. You can use necessary. We think we need two types of cargo and a crew so you can get a larger volume of material down, and with the reusable vehicle you can take multiple trips. So we can't land on Mars right now anything heavier than about 1 ton. Everybody says, all the engineers are saying that is true. We have not developed the technology to land anything on Mars functional heavier than about 1 ton right now. Before you can do that, you have to start development of this technology now, not 1 year before your first Mars mission. This is a long lead time item and process. You have to actually do physical tests in the Earth's atmosphere. There's no combination of equipment right now that can land even a 10-ton payload on Mars right now, much less crew vehicles and cargo vehicles, which are in the range of 60 to 200 tons, which is 2 orders of magnitude larger than what we're doing now. And the leaders in the field confirm this. Some of these people, like Robert Braun, are from Georgia Tech and is currently NASA Chief Technologist. Robert Manning is a chief engineer for the Mars Science Lab Rover and was previously Mars Program Chief Engineer at GPL. A lot of this information has come from papers by them and their colleagues or interviews with them. And this problem has only really been studied for about 5 years. Here is the 850 kilogram, the current Mars rover. You can't actually see that. What this is showing is a 15-foot diameter heat shield to land an 850 kilogram payload on Mars. That gives you some idea of the problem. So we have a bunch of different kinds of technologies to do this. We've got the rigid aeroshells. We've got the inflatable and deployable aeroshells, balloons, decelerators, supersonic retropropulsion, subsonic parachutes, and finally rocket-powered landing and touchdown. And they have all kinds of different schemes to do it, using different combinations of these technologies. Why can't we land big objects? This is hard to explain, so I'm going to go to a little bit more detail. Earth's dense atmosphere slows the re-entering spacecraft to about Mach 1 at 25 miles high, sort of automatically, if you re-enter at the right angle. Mars' atmosphere is like that of Earth at 36 miles high, and its pressure varies by season. That's at the surface. So imagine if the Earth's surface was at 36 miles high with the same density of atmosphere. So the Mars atmosphere does a good job of slowing the objects from, say, 7,500 to about 3,300, or locally Mach 6. Below that speed range, the air is too thin to slow spacecraft enough all by itself. Even supersonic parachute-type systems like balloons can't work at speeds much over 1,100 miles an hour because of thermal and dynamic turbulence. If you're doing a real slow repeated re-entry, like a balloon, like it's just been shown, where you're not heating the surface, you can get away with that. But most for a specific landing point, you have to land at a specific point, and you can't afford a super slow descent. For a 100-ton cargo lander, the subsonic parachute would need to be 300 feet in diameter. It might be too heavy to use effectively. It could take too long to open, and it might frequently fail to open properly at all. It then would have to be disposed of, and it couldn't be reused in the next trip. And you can't make parachutes at Mars. You might also need two parachutes, one supersonic, one subsonic. And this goes into some explanations. There's a thing going on a balloon-like system called a hypercone, which is deployed behind your large spacecraft and is made out of fabric. So you need a whole bunch of combinations of these things to do the job. And unfortunately, I have to go through this real fast because I only got 30 minutes. So some of the problems: you need a full heat shield to shield your equipment that you're going to land on the surface and the crew from the heat of re-entry. We're glad that Mars has an atmosphere, but if Mars had no atmosphere, it would be easy to land on. It would just take a little more fuel. On an airless Mars, the descent rocket engines would fire continuously from orbit down to the ground, just like landing on the moon. With an atmosphere, the descent engines cannot fire during the peak period of re-entry. However, they may be able to fire at the end of re-entry, starting at once you reach down to about 3,200 or about Mach 6 locally. It still seems awfully fast, but you remember it's fairly thin air. This is called supersonic retropropulsion. It's now being taken seriously. It requires rocket thrust firing directly through the heat shield and against the supersonic flow of air pressing against the base of the vehicle as it comes in the atmosphere at the proper angle. The rocket engines must be fixed in position with the nozzle ends flush with and sealed to the heat shield, and thus they cannot gimbal for steering. Steering during re-entry and landing must be done by varying the thrust of a set of engines. This diagram is actually right here, and this is actually showing the shock wave of the re-entry flow hitting the shock wave of gas. Almost no physical testing has been done on this at all. We think maybe that angling the engines at an angle away from directly back will work better than angling them directly forward. But to prove this, you have to do physical tests.
Oh, you don't have your power.
Well, this is not my laptop. It says it's low on power. Do we have a power plug? Somebody can plug the power in? Now you see a loose plug.
Like
Okay, let's plug it in.
Yes.
Just give me the plug.
More voltage.
Okay, let's continue. You know, the computer, Murphy, the computer's waiting. Okay. So it requires actual suborbital tests like this of several different types and configurations, plus heavy computer simulation before you do the test to see what's the best way to do it. And then you need test suborbital tests at the proper altitude in the Earth's atmosphere to prove. You only need maybe 10 seconds of testing. You know, you could probably get